so if fx, we know fx belongs to t, right? Fx belongs to t. We know fy belongs to t. So their product, we've just shown their product. The product is equal to that, and we know that belongs to t. Therefore, this belongs to t. So the product of these two belongs to t. Okay. So for these any two in t, the product belongs to t. So we've got closure now. T is closed. The product of any two elements of t gives you something also belonging to t. Right? So we have closure. Right? So we've got two of the properties. Now let's try the inverses. Okay. Take any element belonging to S. Now S is a subgroup, so it's a group. Therefore, this X will have its inverse also belonging to S, right? Because S is a group. So this is X. Its inverse will belong to S also. Now, if X belongs to S, f of X belongs to T. Now, X of inverse belongs to S, because S is a group, subgroup. Therefore, f of X inverse also belongs to T, right? Because this belongs to S. Therefore, f of it belongs to T. Now, the inverses map homomorphically. Inverses map. Okay? So f of the inverse is the same thing as the inverse of f of X. Right? That was one of our recent theorems. Now we know this belongs to T. It's here, right? But this equals that. Therefore, the inverse of f of X belongs to T, because this does, and these two are equal, right? So the inverse of f of X belongs to T. So for any X here, you'll have an f of X here, and for any f of X here, its inverse of f of X belongs to T. So for any element here, you'll have an inverse in the same T. Okay, so the inverses belong to T as well. So we've got all three. The unit, closure, and the inverses. Therefore, T is a subgroup, not just a subset. Okay, so we've proved that. Okay, now the second question, question 3, is pretty trivial, so I'll just do it quickly. It's just a few lines. I was debating whether even to bother with it. Anyway, so let A be any element belonging to some group G, and you've got some homomorphic mapping, mapping the integers, just Z, with binary operation plus. Right? So you're just adding integers. Okay? So you're mapping integers into G, whatever. Doesn't say what G is. It doesn't matter. Okay, so here's the actual mapping. So f of n, so n is some integer belonging to G, right? Right, and it's just defined as a whatever this element is, whatever its type is, to the n. Right, so f of n is equal to a at n, this element to the nth power, and you're asked to show this this mapping, this function f is homomorphic, which I just shortened to homom. Right? Well, to prove homomorphism, it's just the f of mn equals f of m, f of n, sort of thing. So here's f of m times f of n. We'll try to prove that that's the same as f of mn. Well, the binary operation is now plus, so we can write it that way. All right. Well, what is f of n? Well, I'll just put an m here, so we get a to the m. Right, there it is there, and f to the n. Well, that's the same. So a to the n. Okay. Now these are just integers, and they're just exponents, so you can just add them as indices, right? So this just becomes a to the n plus n. But what is this? Well, from here, if this is n plus n, that'll be n plus n. So it's just f of n plus n. So this equals that, and there you've got it, right? So pretty easy. Okay, third question, which is question 5 in the text. You're given two homomorphisms, F and G, two mappings. And F maps the group G into H, and G, a second mapping, maps H into K. Okay, so it's sort of like a stepping stone, like a two-step mapping. So, and you're told that both F and G are homomorphic, right? So you can probably see where this is going, what you can just read, I guess. So if you perform what's the word, composite, one after the other. If you perform the composite function, like F followed by G, remember the inner one, the one on the right goes first. So you perform F first, and then you do G. So that composite function, FG, or reading from the left, GF, that maps G to K, right? So you do F, first maps G to H, and then you do G, which maps H to K. So effectively, FG together maps G to K. You're to show that this composite function is homomorphic, right? Now, to do that, what that means is, again, it's this kind of trick. So you can translate that to show that this is homomorphic. Effectively, you're doing this. So take any two elements of G, your starting group, your domain, and you need to show that. So if GF or FG, whether you're reading from the left or from the right, I'll just say GF. So if you need to show that GF of xy is equal to GF of x, GF of y. If that's true, then this GF is homomorphic. Okay? Alright. Now we know F and G separately are homomorphisms. F's homomorphic, G's homomorphic. Right? So now let F of x be equal to some member of H, right? We're mapping elements of G, group G, into elements of group H, right? So for x, there'll be some H that gets, well, that's the image of x, right? So f of x will be equal to h, which belongs to big H, your group. And similarly, f of y will map into some little k, which is a member of, oops. X and y belong to G, right? So f of y will map usually into some other element of H. Okay, so you've got f of y equals k. Now similarly, let g of h will map into something in k, right? So if we're mapping the member of big H, which is little h, it will map into some little k, okay, belonging to big K. Right? So you've got something like that. And some little k, this k here, when we map it by G, it will map into some other member that belongs to K. Right? So we've got G of K is N. Right. Now we can start rewriting this. Now we'll use these and rewrite this. So we're trying to show that g of x, g of y is equal to this. Right? If we can do that, we've proved it. All right. So let's rewrite this. So g of x times g of y is what? Well, what is f of x? F of x is h. Right? So we've got g of h, and fy is what? K. So we've got g of k. Right? Now G is homomorphic. So we can rewrite this as G of HK. Right? But what is H? H is f of x. So for this h here, substitute f of x. And what's little k? Well, it's f of y. So for this little k here, substitute f of y. And f of... But f is homomorphic, right? So f of x, f of y, you can rewrite as f of xy. Now you've got a g outside it, so you've got gf of xy, right? gf of xy, and that equals this, right? So you proved it. Right? That's the end of problem solving, and hence the end of lecture 18 on homomorphisms. And we are now only one lecture away from the end of the course, which consists of 19 lectures. So getting pretty close. Now, I'm debating whether I should mention it now at the end of the next lecture. I think I'll wait till the end of the next lecture. It's more a general type comment. So that's the end of lecture 18. Until next time for lecture 19. Ciao.